Alrighty. So, go over the stuff for this unit exam here. Okay, first thing we talked about in this unit was climate. Okay, the things you need to remember about climate. The difference between the components of climate, temperature, precipitation, light, and wind, and the factors that affect climate. Okay, and those are the things like latitude, altitude, presence of mountain barriers, closeness to water, all that kind of stuff. Okay, you got to make sure you keep those straight. Okay, because a question may say talk about the components, or another question may say talk about the factors, and if you get them mixed up, you're not getting any marks. All right, so make sure you keep those ones straight. Okay, now how am I going to ask about this? Probably in the same way that our climatograms activity worked. Right? I'm going to give you a specific location, and I'll show it to you on a map, and I'll say, tell me what you think the climate of this place will be like, and what are the main factors affecting it. Okay, something like that. So you don't have to be a geography whiz to answer that question. I'll show you specifically where I'm talking about, and I've picked a place that you all know, okay, or at least you'll be able to take a really good stab at. And then you got to tell me about the factors and the components for the climate in that area. Making sense? Okay. No, I'm not giving you a copy of this. No. Okay. No. All right. Then we talked about climatograms. Okay. And we've said already that you're going to have to interpret a climatogram. Okay. And that means I'll give you one, and you got to tell me which biome it belongs with, okay? And then you got to explain why, right? In that explanation, you should probably tell me, you know, the bars on this are really high, so that means there's lots of precipitation, or it's really low, so it's really dry, okay? There's no bell curve, so it's near the equator, or there is a bell curve, so it's a long way from the equator, okay? Talk about where the bell curve is, if there is one, stuff like that. So be able to analyze the climatogram and then say, based on my analysis, I think it fits with the tropical rainforest or the taiga or whatever. All right, does that sort of make sense to everybody? Okay, that's how you're going to have to do. That's what you're going to have to do with climatograms. Okay, so that'll be a written response item. Okay. Then we talked about energy transfers. Okay, and we talked about lithosphere, hydrosphere, atmosphere. Okay. There's lots of stuff on this test about that particular lesson. So I'll let you write that down, and then we'll talk a little bit more about how and what, okay, is going to be tested on that. Okay, so when we first started talking about energy transfers on Earth, the first thing we said is what can happen to energy when it strikes the Earth's surface? There are 3 things that can happen to it. Anyone remember what they were? Absorbed is one. Reflected is another. The last thing is done by the little green things. No, we got absorbed. Converted with the process of photosynthesis. Okay? Should we remember the 3 things that can happen to energy when it strikes the Earth's surface? We definitely should. Okay? So, because it's based at those 3 things kind of influence all of this stuff, right? So when energy hits the Earth's surface, it could be absorbed, okay? And the amount of it that's absorbed is affected by this thing, albedo. Okay? Remember that the albedo talks about how reflective the Earth's surface is. The higher the albedo, the more reflective the Earth's surface is. So right now, because it's covered with snow here, okay, the albedo is very, very high, and we're reflecting away a lot of the solar energy from the surface. In the summertime, the albedo is much lower, and we're absorbing a lot more. All right, within the atmosphere, which one of these 3 was the most important for transferring energy worldwide? Okay, convection within the atmosphere, right? So convection was the most important process. The atmosphere was the place or the part of the Earth that was most important. Okay, and we call convection within the atmosphere wind. Okay, and we talked about the wind patterns, which we'll get to here in a little bit. All right, so within the atmosphere, okay, radiation is absorbed. Okay, so the solar radiation coming in gets absorbed. That makes the temperature of the atmosphere go up. Okay, it can be transported by convection, and that convection can sometimes move this stuff. latent heat. Remember that when water evaporates, it takes a lot of energy for that to happen, right? And then it can be transported to other places. Okay? Within the lithosphere, radiation can be absorbed based on albedo, but it can only be transferred by conduction because the lithosphere is solid. Okay? So does the lithosphere have a very big part to play in transferring energy? It doesn't. Okay? Because it can't. Conduction is a very slow and short-range process. Okay? It's the knocking together of atoms. Okay? That does not transfer energy over large distances. Okay? It can do a lot of absorption, but it can't really transport that energy anywhere. All right? And then we talked about the hydrosphere, which again can absorb radiation. Okay? There's convection within it because the ocean currents are examples of convection. Okay? And so lots of things can go from there. And this is where the latent heat comes from. Okay? Because this is the source of the water vapor. Okay? As the water is evaporated from the hydrosphere and goes into the atmosphere, that's where that energy comes from. Okay? So some of this, the recall kind of stuff, will be in the multiple choice. Okay, which one of the parts of the Earth is most important for transferring energy? Blah blah blah. Okay, that could be a multiple choice question. But a lot of this is going to be written response, and it's going to be related to application of what you know. Right? So there could be some questions that say, based on what you know of conduction and convection and radiation, can you build a structure that would do this job? What kind of materials would you use? How would they prevent, or how would they enhance the transfer of energy? Okay, kind of follow me there? We talked about how a quinsy, okay, does a job like that. Okay, because it's white in color, so it reflected stuff, etc. You guys remember us talking about that? Okay, so there's going to be some apply your knowledge kind of questions. There could also be a question that says, talk about what happens to the energy in this situation. So, you know, if we're saying you've got a section of New York City, you know, what's happening to the energy that strikes the surface of the city? Okay, and you would say, well, you know, cities tend to be dark in color. Okay, so lots of stuff would get absorbed. Lots of energy would be absorbed. You know, air around a city often contains lots of carbon dioxide, so lots of the heat would be trapped. Okay, and so the area would heat up quickly and have high temperatures. And you basically have to talk about, okay, the three things that happen to energy: absorbed, reflected, and converted. Would there be much conversion within a city? No, because everything's covered in concrete and asphalt and buildings and whatever. So there's not as many trees and grass and stuff like that as there would be in a natural place. All right, so that's the kind of things you'd have to think of. Does that sort of make sense? Again, you're applying your knowledge of, okay, what happens to light, and then talk about conduction, convection, and radiation as much as you can as well. Question, Joshua? No. All right. Okay. We talked about this just a minute ago. Three things that happen to energy when it encounters any place on Earth. Any place on Earth. All right? Okay? It can be absorbed. And if it's absorbed, there'll be an increase in temperature. Not really, but I'll try. Okay? We also said it could be reflected. If it's reflected, will there be a change in energy then? What do you think? Remember what we talked about? If you don't wrap the baked potato in the right side, okay, of the tin foil, right? It had a shiny side and a dull side. If you reflect away all the energy, do you absorb any of it? Okay, so is there going to be any change in temperature then? Not very much, right? That's why you want to make sure you wrap the baked potato with the dull side out so that it does absorb and increase its temperature. If you wrap it with the shiny side out, it just reflects all the energy away. It doesn't absorb it. It doesn't cook. All right, so things like that to think about there. Okay, so if there's reflection, very small or no change in energy. And if the energy is converted, it's kind of being absorbed, but it's not being absorbed as thermal energy. It's being turned into what? What kind of energy do plants turn the sunlight into? Sugar, which is a form of chemical energy. Okay, so the conversion process is the most important in terms of making energy for organisms on Earth to use. If that process didn't happen, Earth would just be reflecting and absorbing. It wouldn't be doing any converting. Okay, and then there wouldn't be any life. Right? So the conversion process is pretty important. Now, when I ask about this kind of a question, okay, this would be talking about hitting a spot on Earth that would be, let's say, a natural place. Okay, so this place would not be covered in solar panels. Okay, when I'm talking about tell me what happens to the energy when it strikes the Earth's surface. If you say to me, it hits solar panels and gets turned into electricity, I will flip out on you. Okay, we never talked about that. Okay, we're talking about global systems and energy. We're talking about natural systems and energy. Okay, the last time I checked, there were no solar panels sitting outside on the ground. Okay, at least not here. Maybe in California, but not here. Okay, everyone with me there? So if I'm talking about energy and systems, I'm talking about natural systems. Please only talk about natural systems, okay, when we're doing a question like that. Everybody with me? All right, so we said the last thing that can happen is it can be converted, okay? That's photosynthesis, changing sunlight into food energy. Okay? Okay, you might just have to watch the podcast later and get the rest of it, okay? All right, so that's a pretty important process. Okay, now, all of this stuff here relates to energy budgets. Did we talk about those? Okay, the title of the lesson was Energy Budgets, lesson 2. Sorry, 3, lesson 3. Okay, energy budgets. So the energy budget is how much of the energy gets absorbed, because we can use that, and how much of it gets converted, we can use that. The stuff that gets reflected, we can't use that. Unless it reflects off the greenhouse gases and comes back down and gets absorbed. Okay, and then we can use it. We can only use the energies that stay here. Okay? We can't use the energies that do not stay here or that reflect off of the Earth. Okay, so places with a high albedo then are not going to have much energy to budget. Agreed? Okay, so how about a place like Antarctica? Is that going to have much energy? Right? It's covered in ice. Right? If it's covered in ice, we said the other day that the driest continent on Earth is Antarctica. Okay? Because you can't get the water cycle going there. Okay? If there's no energy being absorbed, not only will the ice not melt, but certainly no water is going to evaporate, which basically means the water cycle just stops. Okay? And then you don't get much precipitation. So that makes it very, very dry. Okay? Does that sort of make sense? Right? Does that incorporate the water cycle that we talked about? Okay, so everything kind of ties in a little bit here. That's what this whole unit is about, is tying together all these little tiny concepts, okay, that we've talked about at some point or another. Okay. All right. Now, talked about global wind patterns next, okay? And we talked about some examples of winds, like trade winds, okay? And the trade winds were near the equator, okay? They're easterlies, they blow from east to west, okay? And that is a combination of the Coriolis effect and convection. In your notes, you have a diagram that kind of looks like this, where there's hot air rising at the equator, and then it's moving this way, and there's cool air that's coming back in below it, and then you've got kind of the reverse going on here, and then there's kind of that vortex at the pole, right? And the whole while that this hot air is rising and the cool air is moving down, the Earth is rotating this way underneath it. And so the air that's trying to go from north to south gets deflected, and we feel winds as though they're coming from the east as opposed to from north or south. Okay, that was the Coriolis effect and convection, okay, causing prevailing winds. All right, that is probably something that you'll be asked about. Okay, how do those two processes separately work? and how do those two processes together contribute to prevailing winds. Okay, another wind pattern we talked about was the jet stream. Okay, and the jet stream was really important because it can cause changes in weather based on its location, but mostly it deals with transporting this stuff. Okay, because it tends to move north to south a lot. Okay, and so it can be bringing moisture-laden air, okay, warm, moisture-laden air from equatorial or tropical areas up to more polar areas, okay, and when that happens, then it encounters cooler air and we get precipitation, okay, and we get rapid changes in weather as the jet stream crosses us, okay, so the jet stream can interact, push around, if you will, okay, air masses causing those changes in weather. So that's why the jet stream was important for transferring energy, especially the latent heat. Now, in order for the latent heat to become sensible heat, what does the water vapor have to do? This has to do a little bit with the heating curve of water. The only way to get the energy out of the water vapor is to turn it back into liquid water. Remember, the heating curve said we put energy in, we turn liquid to gas. But the other way, that energy gets released, which is why steam burned you worse than water. You guys remember us talking about that? Okay, so that latent heat, the only way that gets out is if the warm, moisture-laden air encounters cooler air, and then the moisture condenses and it releases all of that latent heat and warms up the other area. So that's why the jet stream is important for transferring energy from the equator to the north as well. All right. So just kind of what we were talking about there the last couple minutes there. Okay, so high speed, high altitude, energy transfer from different latitudes. So essentially from tropical areas to northerly areas, and vice versa. Okay, we saw that the jet stream can also drop from a polar area and go down to a cooler area. Okay, and that can cause changes in weather as well. Any questions on that part of it? Okay. If there's one lesson in this whole unit that had more information in it than any other, it was that one. Okay, lesson 3 and lesson 4. Okay, were the two big ones because it talked about all the methods of heat transfer, conduction, convection, radiation. It talked about how those interact, how those produce changes in weather, prevailing winds, all of that, and all of that gets tied together. So if you're reviewing lessons, make sure 3 and 4 are on your list for big time review. Okay. Okay, then we talked about heat capacity. There might be a multiple choice question or two, okay, about heat capacity, mostly recall stuff like what it is, maybe what the units are or stuff like that, okay, but for the most part, if I'm asking you about heat capacity, you're solving a heat capacity problem, okay, so you got to be able to use E equals mc delta T, got to be able to manipulate it to solve for any one of the parts of it. Last semester, I think I asked people to calculate the mass of something. It was the mass of a pot or a pan. Okay, so it absorbed so much energy and its temperature changed by this much. What was the mass of the pan or something like that? Okay, so that's kind of, it's very much like the questions that are on your worksheet. So what I would say is to practice for that, okay, take out that heat capacity worksheet, and you could see that on there it was like 4 questions asked you to solve for mass, and then 4 questions asked you to solve for specific heat, and then do 1 or 2 of each section. If you can do them, you're set. Okay? Everybody with me there? Right? So that's a pretty easy 5-mark kind of problem-solving question. We want to definitely get those. Okay? And then after heat capacity, we did the heating curve of water. Okay, that was latent heat. Okay, so heating curve of water, latent heat. Okay, energy used, okay, or given off when a state change occurs. So when ice melts, we have to put energy in. When water freezes, energy gets released, and the same thing for when we evaporate versus condense our water. Are you going to get a heating curve problem to solve? Yes. Okay. If you're solving a heating curve question, should you draw the heating curve and identify your start and end points? Yes, you should, because I'll give you a mark for that. Okay, and then show your work for each step and add the numbers up. All the energies from each step, add them up, and you've got your final answer. Pretty straightforward problems, no manipulations involved, okay? But I think it's a 7-mark question on your unit exam. Okay, so we want to get those 7 marks as well, as they're pretty straightforward marks. Okay, so this is basically all in your notes, okay, but just so you get a look at it here. Okay, so latent heat of fusion, that's LF. Okay, that's what happens when it melts or freezes. You don't have to remember the number, it's on the front of the test. Okay, latent heat of fusion is 333 joules per gram, but it's on the front of the test. Okay, latent heat of vaporization, that's the energy used to evaporate or given off when condensation happens. Okay, that's LV, 2,260 joules per gram. Okay, but that's also on the front of your exam, so you don't have to memorize it. Okay, the formulas are also all on the front of the exam, so E equals MC delta T is on there, E equals MLF, E equals MLV, all of that's on there, so you don't have to memorize them. Not that you probably don't already know them off by heart, but okay, just in case you draw a blank. Right, so we said the heating curve, the shape of the heating curve is important. You don't necessarily have to draw the full graph, okay, just draw the shape. Okay, and then you identify your start and end points, and from there you solve the problem. I don't know what these numbers are. I don't remember what these numbers were about on here, guys. Ignore those numbers. I don't know. I don't remember why I put them on there. I must have been solving a problem and just wrote them on. Okay, and then the last things, biomes. Okay, we talked about them yesterday. How are you going to be tested on those? I'll give you a picture and a description of a biome, and you got to tell me in a multiple choice question which one it is, and then in the written response, match up the climatogram with the biome and explain why. Okay, that's it. Okay, that's what's on your test tomorrow. So none of it's really difficult stuff. There's a fair amount of material, but none of it's really difficult. So when you're studying tonight, make sure you go over the skills. Okay, that's the specific heat problems and the latent heat problems, and make sure you think about some situations where the heat transfer stuff could come into play. Okay, that would be anytime something needs to be kept cold or anytime something needs to be warmed up. Okay, something like that. So look at how that might happen. Okay, because there'll be some applier knowledge questions on those. Review your biomes. Okay, pick out some major features of each biome that you might look for. Okay, the picture is really helpful in most of the questions, but obviously you'll want to be able to look at the description as well and go, oh yeah, he's probably talking about this one. Okay, and then again, read over the stuff on wind patterns, okay, Coriolis effect, stuff like that. In a multiple choice question, there'll be 4. No. No, you'll have to know the biomes. Yeah. Well, there's not that many of them. Okay, so no, you do have to know the biomes. You got to be able to recognize them. Okay, so make sure you're ready for that part. All right, other questions? How many people have started the review sheet already? Okay, any questions on the review sheet so far? Rachel? Number 15, okay. Okay, pull it up here. Oh, that's disconcerting. Try it that way. Okay, number 15. Okay, so number 15 is a heating curve question. All right. If we're looking at this, we're saying the amount of heat required to heat 280 grams of ice from minus 28 into steam at 150. Okay, so if we're looking at that in terms of the heating curve here, okay, so we just do a rough drawing of the heating curve. Okay, down here is where minus 28 would be, and up here is where 150 degrees would be. Right? So I've got 1 step, 2 steps, 3 steps, 4 steps, 5 steps. Anywhere where the line changes direction is the start of a new step. Okay, so this is the biggest one that you could be asked to do. It's got all 5 steps. Okay, what formula do I use anywhere where the line is going up? E equals mc delta t, because temperature is changing anywhere the line goes up. Okay, so I got E equals mc delta t. Okay, here I would use E equals MLF, okay, because it's dealing with melting and freezing. Okay, and up here I would use E equals MLV because that's where it's vaporizing. Okay, here is mc delta t. Okay, and here is mc delta t. Now we said here's the 2 places where people mess this up. Okay, they don't mess up this part. But what they mess up is either they use the wrong specific heats, or they use the total temperature change for the whole question rather than the temperature change for each section. Okay, for this part, this E equals mc delta t is only dealing with the ice, and the ice can't get any hotter than 0. Okay, so for this one, what was the mass in that question, Rachel? 280 grams, I think, right? Okay, so 280 grams, okay, times the specific heat of ice, 2.116, okay, and then the temperature change, it started at minus 28. The ice can only get to be 0, so the temperature change is 28. Okay, then we do our 280 times 333 for this step. For this step, I'm now dealing with liquid water, so I still have 280 grams, but now I use the specific heat capacity of water, and the water is going from 0 to 100. So that's 100 degrees. Okay, and that would give me my answer there. Here I would have my 280 times the latent heat of vaporization, 2,260. And up here, okay, I've got 280 grams times the heat capacity of steam, 2.02. And then the temperature change, I think it went to 150. So the temperature change is 50 degrees. All right, but again, the most common mistake I would see would be that people would say the temperature change is 178 degrees. Okay, and they would use 178 here, here, and here, which is not true. Okay, water does not change by 178 degrees. It changes by 100. Okay, the ice only goes from minus 28 to 0, etc. All right, does that answer your question, Rachel? Yep. Okay, any others? Jack? Just the ones you think most impact Okotoks, okay, for number 2. So explain why the climate of Okotoks is the way it is. So first, you got to describe the climate of Okotoks, right? So you'd have to say, Okotoks' climate is relatively dry. There's variable amounts of light throughout the year, right? So we're describing the components here: temperature, light, precipitation, and wind. Wind is generally out of the southwest, blah, 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 right? So you describe our 4 components, and then you say the components are this way because we are far from the equator. We are close to mountain barriers, we are at a high altitude, and we are nowhere near any large bodies of water. These things make temperatures fluctuate, produce low precipitation, etc. Right? So you incorporate the 2 together. Okay? And that question, guys, that was exactly an exam question about 3-4 years ago. Okay? Did I say you were going to have one like that tomorrow? Okay? That was the one where I said I'm going to pick a spot on a map. Okay? So be ready for something like that. Okay? All right? Other questions? Okay, let's give you some detail here. Okay, you have 25 multiple choice. Okay, multiple choice topics. Like we said, there's the biome identification questions. There's some stuff about, atmosphere and hydrosphere and soil layers. So your A, B, and C horizons. There's some stuff in there about the water cycle, components versus factors of climate. More factors, components, lots of stuff on factors and components, albedo, what happens to energy when it strikes the Earth's surface, okay, some stuff about conduction, convection, and radiation, several things about that, okay, more stuff about albedo, more stuff about latent heat, heat capacity, yep. Okay, and then in your written response, okay, there are 9 written response. Okay, and I've told you basically you got your climatogram, okay, that you have to associate. You've got your city and the components and factors. You have global wind patterns. Okay, more stuff on global wind patterns. You've got energy budgets. You've got some heat transfer stuff, convection, convection, and radiation. Heat capacity, latent heat, and then an apply your knowledge with latent heats question. Okay, that'll give you a pretty good idea what's on there. Okay, unless you really dawdle on any of the questions, I don't think time is going to be a factor for anybody. Okay, I was done the key in 15 minutes, which means it's really short. Okay, so just answer the questions thoroughly. You have time to do so. Okay, think of everything you think could be part of the answer for a written response question. Okay, incorporate as many ideas as you can into your response, would be my suggestion. Okay, make sure you bring your calculator for tomorrow because you won't be able to use your phone, and you've got a latent heat question and a specific heat capacity problem to solve. Okay, so make sure that you do that. You don't need a ruler or anything, so just your calculator and something to write with will really be all you need. Okay. All right, you have a review sheet there, and you have a half an hour left in class to do your studying. Yep.